Okay, so let's start the second session. So for this session, we'll have 3 paper presentations. The first one is Ontology for Industrial Engineering, a Dolce compliant approach, will be presented by Walter Turkage, who is already online, and also Emilio. So both of them will present this paper. So I give the floor to you, Walter.
Hello, good morning. Thank you for the introduction. So
We
let's
don't hear
start.
you.
Yeah, can you hear me now? Hello?
Please check,
Hello?
Walter, to turn on your mic.
Yes, it's on. Hello?
Wait a second, because we tested a moment ago and it worked. So maybe now like this. It's always like this. Live.
Hello? Hello?
Yeah, now it works.
Can you hear me now?
Yeah, it's perfect. Okay,
Great.
so floor is yours.
So thanks for the introduction. So let's start with the presentation that I will do with together with Emilio. So it will be hybrid. And so let's see if the slide move. Okay. So the first part is more about introduction and motivation. So it's all about concept that we know very well. So we are not going to spend much time about it. It will be mainly pointers to what was before this presentation and what will be in the next few days of this workshop. So industrial motivation, digital twin. So the keynote speech was quite inspiring and also mentioning this concept. So to make digital twin, we need digital representation. And so some key requirements, of course, are a reference data model, instances and measure data, and then, of course, methods and tools that are able to consume and produce this data. In particular, reference data model is a fundamental requirement to have a working digital twin, and sometimes it's quite neglected, and that's why I wanted to stress this point, and that's one of the key motivation of the work we are presenting today. So without a reference data model, it's not really possible to have a usable and above all reusable digital twin that is able to support engineering activities. Some of the scientific motivation, well, again, it's something quite trivial for this community. I just wanted again to just take note of them. We are interested in semantic meta modeling, of course. In engineering, and in particular industrial engineering, we need to deal with heterogeneous data. And so again, I recall the figure in the keynote speech of this morning by Stefan Grimm, with a collection of different domains that must be connected all together. Data distribution, we have multiple data sources and silos where we store and retrieve data. Modularity, we want to reuse as much as possible technical standards. And of course, to support our activities, we use more and more digital tools. So we want to facilitate interoperability. And it's not to be repeated, we have important ongoing initiatives like OntoCommons and IOF that are organizing these important workshop in these days. Graphical representation, to stress again what I was saying. So at the core of everything, in our view, there is an ontology-based digital factory twin, but it could be also product twin, whatever we need in the scope of industrial engineering, to support interoperability, as I just said, but also to guarantee that the evolving models, digital models, are coherent inside them, but also in relation with the other part of the overall digital model. And not to be forgotten, of course, we need to synchronize what is on the digital world with what is in the real world. So synchronization between real and digital factor. Going to the research objectives. So what we wanted to do with this with work, the goal is the end goal is to have an ontology-based information system for modeling industrial engineering application cases. So here are three of the main cornerstone, let's say, of our work. So we wanted to make something that is practical, and so that was the decision about the computational language, and that's why we decided to adopt OWL with its good properties. Of course, again, we don't have time to go into the pros and cons, but anyhow, OWL is making a good compromise to make things practical and applicable. Then about the scope, we wanted to support both the design and planning phase, but also the execution and management of production system with their assets, so products, processes, resources, facilities, and so on. And to better explain this, we define a list of competency questions that again can be grouped in the design part and the execution part, but not to be again neglected is the link between the two sides. That is very important, and sometimes we are more focused also in some application to just one of the two sides. And then, of course, since we are, let's say, scientists, we cannot build anything without taking into account the background contributions. In particular, we see about the upper level ontology, and also it's the name of the title of the work, and we decided to use in particular Dolce. And later, in a few seconds, I'll give you motivations about this. So, competency question. So, about the industrial domain we are interested in. Again, for the competency question, you see we group them in the orange one that are about design planning, and the blue one that are more about execution and management. So we are interested in describing artifacts. So as a product as design, artifact as design, together with the process plan and activities. But also we want, of course, to describe the physical artifact, so the artifact as produced, together with the occurrences of the activities and specific manufacturing operation. And then the green part, so how we can link them. So how we can link the description of an artifact with the realization of the artifact, so the physical realization of the artifact. Also, about the production systems and resources, how can we make explicit which are the production resources that we need to execute an activity? And then on the execution phase, which is the schedule? So which specific physical production resource we decide to use to execute a manufacturing operation, so the occurrence of the activity. These 10 competency questions that we put in the paper for is just a little small portion of what we really need. Here in this slide, we listed some other of them that are also related to other subdomains. But again, this is just to give a glimpse of what how complex it is to find also the competency question for this industrial engineering domain. Then, still related to competency question, still making an effort to make things as practical as possible. We focus our attention on a specific use case that is the result of another other research and project activities. In particular, this is about an assembly line producing a hinge for pieces of furniture. So I think that most of you know what it is about. Maybe you also built by yourself these kinds of pieces of furniture. And the description of this use case can also be found online. You see the links in some of our slides. And the description, of course, relates to the building products, processes, machine tools and robots, and in particular, the relations between all these assets. Then, what else? About let's move to the background contribution. The title already says that we are focusing on Dolce. Of course, as any decision, scientific and industrial decision, there are pros and cons. Some of the pros, of course, is that it's the work about Dolce has already started since about 20 years. There is the ongoing effort to make it part of the ISO standard 21838, and some of the, let's say, limitation, let's say, but not, let's say, limitation, more hurdles, obstacles at the moment is that we still don't have a stable out version of Dolce. It's a work in progress. And the main reason why is that it's difficult it's not that easy to move from a first order logic ontology to an owl ontology, since Dolce was, let's say, was born as a first order logic and then a common logic in the ISO, in the recent ISO standard. Other background contribution is IFC-OWL, that is a well-established ontology based on the IFC standard. In this case, this is an ontology that is automatically generated based on conversion pattern. IFC is, again, we have pros and cons. It's covering a wide set of domains that are relevant in industrial engineering. But a big lack, a big cons is that we are missing a clear ontological commitment. It's a very huge, we have a very huge taxonomy and structure that is difficult to really to navigate and understand fully. Another background contribution is a factory data model that is a scientific contribution that we've been working on in the recent year, trying to integrate several ontologies that are based on standards or conversion of standards. So, for example, we can mention SOSA SSN by W3C, but also the previously mentioned IFC-OWL. And this is a prototype, let's say, architecture of ontologies that so far has been used mainly for academic purposes, but also for some, let's say, test in industrial settings. What is still missing is the use of a single upper level ontology. So this is a limitation that we currently have in this contribution. And so, putting everything together, here we have the Dolce meets industrial engineering. So these are our goals and main decisions. So why did we select Dolce? Well, because it has some important enablers that we think can help to well model industrial engineering setting. So distinction between material and produce object. We can handle qualities and quality values. And also we can separate the description part. So as I said before, the product design and the product as produced. Then Another important motivation is that we wanted to take advantage of the ongoing work related to the HAL version of Dolce. And not the last, we want to exploit as much as possible the expertise of the co-authors of this work. So the next few slides will go more into the details of this Dolce engine. So this domain ontology, or maybe we can also call it a mid-level ontology that is based on Dolce for industrial engineering. So we see taxonomy and relations, and then a few examples of how we can instantiate Dolce Eng with reference to the industrial use case that I briefly presented before. So now I can give the mic to Emilio.
Yes, Walter, thank you. I hope the people can hear me. So if you move, exactly. Okay, so this is the taxonomy of Dolce that Walter showed before. So as you can see here with the yellow classes, these are the elements that we put in order to extend the ontology to be applied to the manufacturing, to the engineering domain, indeed. And for the moment, I mean, you can see that there are only a few classes because we just focus on some preliminary work based on the requirement solicitation. And I mean, what is relevant to note here, also with respect to what we will say before, we will say afterwards, is just notice the difference between the elements in blue, which are the physical level. So you have the activity occurrence, or you have the artifacts, so you really have the things there in the world in your manufacturing site. And then you have also the level of the description, where you have let's say, technical description describing either the product or the manufacturing plan, because we need to take into account both aspects of engineering knowledge. I think that this doesn't matter, right? Walter, can you move to the next slide? Okay, so for the relationships, for the relationship that we use in order to represent the ontology, again, I mean, you have reflected here with the colors the distinction between the description level and the physical level. And then in green, you have also the links, let's say, between them. So you want to say at some point that, for instance, a technical product that you have manufactured satisfy your design requirements. So we have a relationship which in Dolce is called classification, which is helpful to make the link between the description level and the physical level. I will now discuss a bit more in detail how we represented a specific type of relationship with respect to the decomposition of artifacts. And something which is relevant here, oh no, sorry, Walter, can you come back? Thank you. I mean, what you can notice here is that we have different types of relationship in the ontology. So we have, let's say, standard OWL properties, which are binary relationship. And then we have relationship which we are reifying. So we are treating them as classes. And then we have a relationship that we call constant. And why this is necessary? Walter, please, next slide. Well, basically because we need to find a compromise between the conceptual expressivity of the ontology and then the modeling powerful, let's say, of the language that we are using. So in this case, OWL, which, as we know, it's restricted to binary relationship. While when we work with time constraints, we mostly need to have at least a ternary predicate, because we want to say that a relationship holds at a certain time. So for instance, if we have partout between objects, we say that X is part of Y at a certain time. The same for participation, we say that an entity participates in a process at a certain time, and classification, your entity satisfy a design requirement at a certain time again. From an engineering point of view, reference to time plays a fundamental role. For instance, assembly modeling, because object can change. You can host different components at different times. For process plan execution, because you need to say, I'm using this resource in this process at this time. And for classification, because of course, I mean, maintenance teach us that objects do not always satisfy the requirements that they should satisfy. Please, next slide. So in the knowledge engineering community, these kind of problems are very, very
So it seems that in France they have technical problems. PC1, okay, is back. Emilio is still muted. PC1 is still muted.
Okay, now I think that it's working again. Okay, let's continue. So, Walter, I was presenting this slide. Maybe we can move to the other slides. Okay, nice, thank you. Okay, so the second pattern that we use is this of where we have relationships which are called constant, let's say, relationship. A constant relationship is a binary relationship, so it's treated as an object property, but it means to hold for the entire life of some of its related. So, for instance, a relationship is constant proper part of, which tells us that X is proper part of epsilon for the entire life of epsilon. Okay, so epsilon is a whole entity which cannot change its parts. Of course, I mean, this is a trade-off that we have to take sometimes. How this could be used in engineering? Well, if you have unreplaceable components, so you can say, okay, these components are essential for the object. The object cannot lose these parts. In our case, I mean, we assume that the methodological structure of description is invariant through time, so description cannot change with respect to parts. And then for in application context where you do not take a diachronic perspective. So simply you abstract from time and you say, okay, let's skip time restrictions. Okay, please move to the next slide. Okay, so now for the use case instantiation, I mean, this is the use case that Walter was presenting before. I will quickly go through the titling task, which is a task within a more complex manufacturing plan, which has outcome the hinge that Walter was telling you before. And again, here what is important to take into account is that in order to represent the example, we need to represent the design level. So all the description about this object and what's happening in the manufacturing site, the execution level, so the physical object themselves, and then the relationship between them. So the description level and the physical level. Okay, for the next slide. Okay, so here we don't go into the details. I mean, this is let's say a way of formalizing this case using a first-order logic syntax, which is equivalent to OWL, because you can see that we use only very simple modeling elements, binary relationship especially. And for instance, here, this is at the level of the description. So if you have a look, if you just have a quick look at the resource, okay, this follows again. It says that our activity, so in this case, a titling, has a resource requirement, which is a technical artifact description. So this tells us that our plan requires a certain type of resource. Okay, next slide. Then at the classification level, so we make the link from the artifact. So we go from the description level to the physical level. Again, if we have a look at the resource here, we have now a reified relationship, which tells us that the description that we saw before, it's satisfied by a certain entity, which is a physical object. This is a technical artifact. So we are saying that we are taking into account a physical object, which is compliant with the description that we saw before, and which is related to the activity. Okay. Next slide, please. And then finally, at the manufacturing execution level, I mean, we have all the participation relationship, which binds the object in the work, the physical object in the work with the process. So we have again here reified relationship because we need to take into account time. And now we have the tightening, which is the activity, the physical activity occurring in space-time. Which has as participant at a certain time the machine which I was showing you before. And then all the relationship follow the same idea with input and output constraints which are formally represented in the paper. Okay, I mean, now we don't have time to go into the details, so let's move to the conclusion, and then we can discuss if there is anything that you like. So we had this ontology where, I mean, we show the use of Dolce for the engineering domain as a preliminary work. There is still work that has to be done. We started testing the ontology, but of course we need to push forward our analysis at both the technical level, the conceptual level, implementing also the ontology in the system that are especially developed by Walter in the context of this research work. Thank you very much.
Thank you. So if there is any question? Yes.
Maybe, so thank you, Walter. My question is about the competency questions that you had. I think it was the very first one. Could you maybe go to that slide that shows the competency question? There was one that was really broad, something like which resource offers the right function or something. Which production resource is needed to execute an activity? I was wondering, like this, to answer that question, it seems you.
Now starts again. Yeah. Are you now there?
Yes, now I can hear you. I missed the question by, I think it was Stefan. Stefan Green.
Okay, let me just repeat the question. So the CQ competency question, which production resources needed to execute an activity, seems to be rather broad. So it seems to require a complete algorithmic solution that really compares like an offered function from a resource to your requirements and so on. So how can like a simple competency question, which I understand is realizable by a Spark query from the ontology, answer such a big problem? So.
Yes, you are totally right. This is a really quite synthetic competency question, but in the background we have more specific and technical questions that are also related to the capabilities of resources, and this is something we've been also investigating in another previous paper, and we are still. Of course, it's still a work in progress, but yes. But still, also based on the past experience, still we can try make an effort to put everything together so that in the end we can answer the question, a simple question like, is this machine, or better, this set of artifacts of machines and fixtures or whatever able to execute a specific activity? Of course, this is very broad, as you said, but if we make things, let's say, tidy, then I think it would be possible to have a Spark query like this that with some nested checks that are feasible also from a more practical perspective.
Okay, thanks.
Thank you. Is there any question online? No. So I have one. So usually, I mean, in digital twin, everybody is talking about digital twin today. And from different perspectives, people are working and addressing digital twin with different manners. So, and usually I have this question: what is the added value that you are dealing with digital twin through semantic models? So if we compare, I'd like to see, okay, if I deal with digital twin to present those models with different aspects or with different methodologies, and the difference when I use ontology to do that.
I think that this is again a question for the domain experts.
Yeah, so I think this very again, synthetic slide is somehow summarizing. So I think, of course, it's I would say that ontology can be an added value, but not a necessary requirement, because again, we know that there are people working with digital twin that are not employing ontology, so it must be feasible to do it in other ways. But still, I think if we want to enhance the digital twin, again, with the ability to properly represent heterogeneous domain that are related to the specific focus of the digital twin, or even better, something that is related but not yet enabled by the specific application, then ontology can play a key role. But still, we are on the edge of, let's say, early adopter, or on the edge of this technology. So still, we don't have full demonstration of what is actually the potential of using ontology in this domain. But I think that what I listed in this slide, it's quite a decent summary of which are the potential benefits of using ontology to represent a digital twin, and let's say give a boost to digital applications that are based and exploiting the digital twin.
Perfect, thank you. Is there any question?
One question, do you have time?
Yeah, quick one.
Yes, so you showed some reification over time, and then I think that helped you to describe the plan and the actual processes at the same time with the same kind of model. But then plan also have some kind of other modalities, like say you should do it, I mean, kind of, or you may do it, kind of deontic type of modality involved in there. Did you think about how to express those things?
Well, I mean, I would say that from the logical point of view, these are relationship or modalities that cannot be expressed indeed, because the logic does not allow that. I mean, I don't know whether if this is really needed when I try to simulate, let's say, this kind of constraints. But even here, Stefan maybe can add a comment if you like on this. No, I mean, these are the limits, I think, of the language. There is not much, I think, that one can do in this. Maybe adding some constraints could be a kind of solution with the shuffle.
I mean, actually, as you did the reification, I was thinking that can the reification be extended to capture these modalities?
Right. I don't know, to be honest. This is something that might be further looked at. Thank you for the suggestion. I don't know whether anyone has comments on this from our side, let's say.
All right, thank you. Thank you very much again. So now we move to the next presentation with Milos Drobanakovic, who will present the Industrial Ontology Foundry.